Okay guys, so these are the final two examples from today's practice. Again, you're using this to check your work and make sure you did it correctly. Okay, but before we apply L'Hopital's rule, again, we're going to want to figure out if this is an indeterminate form. So let's rewrite this as 5 times the limit as x approaches 0 from the right. Again, we want to pull that constant out if we're able to. Tangent of x to the sine of x power. If I do insert a 0 for x, tangent of 0 is 0, all right, because that's sine over cosine, and sine of 0 is 0. So this is going to be 0 to the 0 power. And that's one of our indeterminate forms, right, because tangent of 0 is 0, sine of 0 is 0. So indeterminate, we need to find a way to deal with this. And this is where we're going to want to set up a little equation that for now we can call y, and we can say that y equals tangent of x to the sine of x power. We don't need the 5 because we've removed the 5 from the limit, so at the very end we will put the 5 back just to show that we are evaluating the original limit. But we don't need it right now. We just need to define the part of this that became indeterminate so that we can work around that. All right, and so I'm going to take this out of exponential notation using a logarithm, so I'm just going to apply the natural log here. ln of y is equal to sine of x times ln of tangent of x. Excuse my handwriting here. I'm going to rewrite that. Okay. So now what I can do, something we did in class, if you'll remember, we'll take the limit as x approaches 0 of both of these sides. So the limit as x approaches 0 from the right of ln of y, and the limit as x approaches 0 from the right of sine of x times ln of tangent of x. Okay, handwriting's really breaking down here. Okay, so I'm going to take the limit as x approaches 0 of both sides and maintain this equality. And the way that I'm going to want to handle this side now is I need to turn this into some sort of fraction. So I'm going to move the sine of x to the denominator. And you're going to see me just work with this side for a little bit. So the limit as x approaches 0 from the right of ln of tangent of x over 1 over sine of x. So I've moved it to the denominator, and now I need the reciprocal of sine of x in order to keep this thing intact, and it's got to be the original expression, right? So at this point, we should be noticing that still this would be indeterminate. If I evaluated this limit the way it looks right now, we would be infinity over infinity, still an indeterminate form. All right, so we do need to progress with this. We're going to have to use L'Hopital's rule here. So I'm going to use L'Hopital's and take the limit as x approaches 0 from the right of, okay, the derivative of ln of tangent of x. We're going to need a chain rule here. That's going to be 1 over tangent of x times the derivative of tangent of x. And we know that the derivative of tangent of x is secant squared of x. That's the numerator. And the denominator is really 1 over sine of x is cosecant of x. And hopefully we recall that the derivative of cosecant of x is negative cosecant of x times cotangent of x. And so what we did there is we just had to recall that that is really cosecant of x. And if you take the derivative of cosecant of x, you get negative cosecant of x times cotangent of x. It's just an old derivative that hopefully we've got memorized by now. If we haven't, then what you would have done here is you would have used the quotient rule on 1 over sine of x. Low derivative of high minus high times the derivative of low over low squared. And we'd end up here. I'm going to rearrange this a little bit. I'm going to press pause and rewrite this in terms of sine and cosine so that it's a little easier to look at. So you'll see that if we rewrote this in terms of sine and cosine, 1 over tangent of x would be cosine of x over sine of x, because this is cotangent of x. And we also have cotangent of x here, so we have that same term in both of these two spots. Secant is 1 over cosine, so this is going to become 1 over cosine squared of x. And cosecant is 1 over sine of x, so this is negative 1 over sine of x. Now, one more time, I'm going to combine these as much as I can. I'm going to cancel out one of these cosines in my numerator, and I'm going to combine these, so I'm going to have a sine squared. And I'll just explain to you what I did here. This is me combining these two terms, and then I combined these. And then to go from this step to this step, I just kept the numerator and turned this into multiplication and used the reciprocal of the denominator. So I did keep, change, flip, and now it looks like this. There's a little more cancellation that I can do here to make this look nice. Sine of x can cancel with one of those sine of x's. All right, so now I'm just going to scroll down. And so the way this looks now is that I have the limit as x approaches 0 from the right of negative sine of x over cosine squared of x. And now if I try to evaluate this thing, I'm hoping that I don't get an indeterminate form anymore. So sine of 0 is 0. Okay. So this would be negative 0 over, and cosine of 0 would be 1. So that would be negative 0 over 1, or 0. All right, so this thing is approaching 0. But we're not quite done, because remember, what we were trying to find was the limit as x approached 0 of tangent of x to the sine over x power. And we made a statement here that allowed us to just work with that part of our equation, but we do need to solve this part of the equation. So remember that we said that y is equal to tangent of x to the sine over x power. So now I'm going to solve this part of the equation, assuming that everything we did here is correct. That means that all of this equals 0, because we decided that that all ends up equaling 0. So this is now the limit as x approaches 0 from the right of ln of y, and we said that that equals 0. I'm going to use one of my properties of limits that allows me to take this function ln outside. So it's now ln of the limit as x approaches 0 from the right of y, which equals 0. Remember that y is this. So when I evaluate this, I am evaluating the limit as x approaches 0 from the right of tangent of x to the sine over x power. All right, to evaluate this whole thing, what I would choose to do is raise both sides, or e to the power of both sides. So now I have e to the power of ln of the limit as x approaches 0 from the right of y, and e to the 0. Okay, now since the natural log and e are inverse operations, I now have the limit as x approaches 0 from the right of y equals 1, because e to the 0 power is 1. So what this is essentially saying is that the limit, or what this is exactly saying, as x approaches 0 from the right of, and this is where I'm going to substitute back in my original equation, tangent of x to the sine over x power, tangent of x to the sine of x power equals 1. All I've done is resubstitute this back in for y. And so I now know that this whole thing is equal to 1. So if my original question was, what is the limit as x approaches 0 from the right of 5 times tangent of x to the sine over x, or sine of x power, and I chose to rewrite it as 5 times the limit as x approaches 0 from the right of tangent of x to the sine of x power, then I've just proven that this is really just 5 times 1, because we showed that all of this, which is all of this, is equal to 1. So then our answer here would be 5. Go ahead and solve the last one on your own. I don't think I've got time in the video here to solve the final problem, but you should be able to do that one on your own, and I'll just post the solution here. So the limit as x approaches 0 from the right of 3 to the x power, when you go through this whole process, you should end up with 3 being your final answer. And what I'll do to prevent this video from being too long is I'm just going to put all the work here, so you'll be able to see it all at once, and it'll just show up. So if you want to pause the video when all the work is here, then you'll be able to see the whole solution. So there's the work. You could just pause the video and take a look at that solution, and that does it for the 5 practice problems on L'Hopital's rule.